Now let's see the airway pressure time curve during mechanical ventilation. So here we have in the y-axis the pressure of the airway, and in the x-axis we have time. So we have inspiration, expiration, inspiration, expiration. And we have 5 parameters, or 5 important pressure we're going to review. So first we have the positive and expiratory pressure. This is going to be the pressure at the end of expiration, and this is a positive pressure. Usually this is equal to the atmospheric pressure. So here I'm going to graph the curve. Something like this, and we are going to explain each part in a second. So positive and expiratory pressure, the pressure at the end of expiration, is going to be like the baseline pressure we have in the alveoli after we take all the air out. So that is this pressure. This pressure is the positive and expiratory pressure. And we can have what is auto PEEP, which is that the patient is retaining air. So this pressure is going to increase. If the patient does not take out all the pressure, the positive and expiratory pressure is going to increase. This is called an auto PEEP. So if we're going to graph that would be something like, instead of the graph ending in this baseline, it's going to have like an auto PEEP, this one, this. So PEEP, the positive and expiratory pressure is this, is the pressure at the end of expiration. If the patient has an increase of that pressure, the auto PEEP, for example, the patient is retaining air, so we have this increase in the curve. This, instead of going all the way down here, it has this. Next parameter we're going to review is the flat pressure. So the flat pressure is a surrogate of the compliance of the lung. So compliance of the lung parenchyma is like how easy is for the lung to expand. So if the flat pressure increases, this means that the compliance of the lung is decreasing. So as flat pressure increases, this means that the lung is not too easy to expand, not too easy to expand. So the compliance is decreasing. Another way to visualize this is with the opposite of compliance, which is the elastic pressure. The elastic pressure is the opposite. Is if we are trying to expand the lung, the alveoli, the lung has a tendency to recoil. We have a tendency to recoil, to collapse. So this pressure, this tendency to recoil, is the elastic pressure. So we can say that flat pressure is equal to positive and expiratory pressure, plus the elastic pressure. This is like, let's say, the recoil of the lung. So this means that the compliance how easy to expand a lung. It depends on the positive end-expiratory pressure, so the pressure that we have at the end of the lung, because we can have an alveoli that is like almost empty. So here the positive end-expiratory pressure is very low, or we can have an alveoli that has more air inside. So here the positive end-expiratory pressure is higher, and the elastic pressure. So how strong is the recoil of the lung? So the compliance is going to be the positive end-expiratory pressure, the pressure inside the alveoli at the end of the expiration, plus the elastic pressure. So how strong is the recoil of the lung as we try to expand the lung. And compliance is the flat pressure is a surrogate of the compliance. So if we graph this here, we have the flat pressure is this. This is the flat pressure. This is if we can like separate. Here we are holding inspiration and holding expiration to be able to measure these parameters. So here this is inspiration, expiration, but here we are holding inspiration and expiration to be able to separate the pressures to see which part of the graph corresponds to each pressure. So this is the flat pressure, and the flat pressure, which is all this, is this, which is the positive end-expiratory pressure, plus the elastic pressure, which is this. This is the elastic pressure. The elastic pressure also is called the driving pressure. And then we have the resistive pressure. So the resistive pressure, this is basically the pressure that we have in the airway that is resisting to air entering to the airway. So this is the pressure in the airway that opposes to air coming in. So here we have, here is the trachea, here is the bronchi, and here the lungs. So if we have, for example, a mucus plug in here, we are going to have resistance for air entering to the alveoli. So as air comes in the trachea and then to the bronchi, if we have this mucus plug, this is generating resistance for air to getting inside. Or if we have a very narrow endotracheal tube, this generates resistance as opposed to a larger endotracheal tube. Or if the endotracheal tube is kinked, this generates resistance. So the resistive pressure is the resistance in the airway that is opposing to air entering to the airway, and this is this part. This is the resistive pressure. And so we can say that the positive inspiratory pressure, the peak inspiratory pressure is going to be the sum of all these. So peak inspiratory pressure is the pressure at the end of inspiration. So this is the peak pressure, and so peak pressure is equal to how easy is to expand the lung, which is the flat pressure. So peak pressure is equal to the flat pressure plus how the resistance that we have here in the air. So how difficult is for the air to get inside the lung. So plus the resistive pressure. Plus the resistive pressure. So the peak inspiratory pressure, or the pressure at the end of inspiration, is equal to the flat pressure plus the resistive pressure. And we said that the flat pressure is equal to the positive end-expiratory pressure plus the elastic pressure. So the peak pressure is equal to the positive end-expiratory pressure plus the elastic pressure plus the elastic pressure plus the resistive pressure So for example, if we have mucus plug in here, the resistive pressure is going to increase, and if the resistive pressure increases, the peak inspiratory pressure increases. So it's going to be more difficult to find the pressure at the end of inspiration is higher, but nothing happens to the compliance of the lung in the case of increasing resistive pressure. So the flat pressure is going to be the same. The resistive pressure increases and the peak pressure increases. On the other hand, if we have an increased elastic pressure, in other words, if we have a decrease in compliance, for example, an stiff lung. So we have an stiff lung, this is decreasing compliance. We have an increase in elastic pressure, or we can have an increase in positive end-expiratory pressure. This is going to increase the peak inspiratory pressure. So if this increases or this increases, the positive end-expiratory pressure is going to increase. So here this is during inspiration. This is during expiration. Here we are holding expiration to be able to see to separate the pressure, because all this is the peak inspiratory pressure, which is divided in resistive pressure, flat pressure, which is all this, which is divided in elastic pressure and positive end-expiratory pressure. So positive end-expiratory pressure is the pressure at the end of expiration. The flat pressure is a surrogate of the compliance. The compliance is going to be the positive end-expiratory pressure plus the elastic pressure, which is also called the driving pressure, and the resistive pressure is the pressure in the airway that opposes to air entering into the lung, and the peak inspiratory pressure is the pressure at the end of inspiration, which is the sum of all this. Is the sum of the flat pressure plus the resistive pressure, but the flat pressure is the same as the positive end-expiratory pressure plus the elastic pressure plus the resistive pressure.